Hey AP Statistics, welcome to section 12.2, our final section on transforming to achieve linearity. By the end of this section, you should be able to use transformations involving powers and roots to find a power model that describes the relationship between two quantitative variables and use the model to make predictions. You should be able to use transformations involving logarithms to find a power model that describes the relationship between two quantitative variables and use the model to make predictions. Use transformations involving logarithms to find an exponential model that describes the relationship between two quantum variables and make predictions, and determine which of several transformations does a better job of producing a linear relationship. So in this section, we're dealing with nonlinear relationships here, so we can see a nonlinear relationship in this example. It's a fun website to check out, gapminder.org, if you haven't checked it out. I've got a lot of data there. So in this case, they've got a bunch of countries, and then they have the income per person graphed here on the X, and then the life expectancy here. And we see very clearly there is a curve to this data. They also have the size of the dot is like the size of the country. So kind of an interesting additional data point or data value included in there. So for instance, yeah, we see, Qatar here, which is way up there in income per person, and then, their life expectancy, but it kind of, it's got that curve to it. All right, so and the color each circle indicates the geographic region in which this country is located. Size is based on the population. Bigger circles, bigger populations. So the relationship between life expectancy and income here is not linear. We can straighten things out using logarithms. So on this actual website, you can change the x-axis from income person to logarithm of income per person. And then all of a sudden we see this nice straight linear relationship. And so that's one thing that we can do to help straighten data. So applying a function such as a logarithm or a square root to a quantitative variable is called transforming the data. Transforming data amounts to changing the size of a measurement that was used when the data were collected. So for instance, consider the power model in the form y equals a times x to the p. So this could be a x squared, x cubed, x to the fourth. It could even be like a square root function. Something like this is a power model, and then you have maybe some coefficient there. If we transform the values of the explanatory variable x by raising them to the power p, so if we raise them to whatever that power was, then we graph the points x to the p and y. The scatter plot should have a linear form, so if we actually graph those points, squared or cubed or whatever it is, and then with y, we end up with a linear relationship. It's just times whatever that constant is. So for an example here, imagine that you have been put in charge of organizing a fishing tournament in which prizes will be given for the heaviest Atlantic Ocean rockfish caught. You know that many fish caught during the tournament will be measured and released. You also are aware that using delicate scales to try to weigh fish that are flopping around and moving on a moving boat will probably not yield a very accurate result. It would be much easier to measure the length of each fish while on the boat. What you need is a way to convert the length of the fish to its weight. You contact the nearby marine research laboratory, and it provides reference data on the length in centimeters and weight in grams for Atlantic Ocean rockfish of several sizes. Here is a scatter plot of the data. Note the very clearly curved form. So we've got a curved relationship here. We've got lengths and weights. And so that's what we get here when we're plotting weight based on length. That's what we want to do. We want to predict weight from length. Because the transform made the association roughly linear. Sorry, did I miss? Hold on a second. All right, so this is the bit that's missing. Because length is one-dimensional and weight, like volume, is three-dimensional, a power model of the form weight is equal to a times length cubed. It's kind of like your density. Should be described the linear relationship. Here's a scatter plot of the weight versus length cubed. So now on this x-axis we have length cubed and weight, and we actually see we have a linear relationship between length cubed and weight. And so then we can get back to our slide here. And so because the transformation made the association roughly linear, we used computer software to perform a linear regression analysis of y equals weight versus x equals length cubed. And so give the equation of the least squares regression line to find any variables you use. So we have this, our coefficient on, and then this was length cubed. And then we were predicting weight, and then we had our y-intercept and so on. So we can create that equation from that, and so that would be predicted weight is equal to 4.066 plus 0.0146 times length cubed. And so notice that we actually end up having a nonlinear relationship, but we used linear regression to figure that out. Suppose a contestant in the fishing tournament catches an Atlantic rockfish that is 36 centimeters long. Use the model from part A to predict the fish's weight. So we'll just plug in that 36, cube it, and multiply and add, and you get a predicted 688.9 grams. So that is a way that you can deal with this. So consider a power model in that same form, y equals a times x to the p. So you could graph the points x to the p if you know whatever power you're supposed to use, and that should produce a scatter plot in the linear form. So in that case, length cubed. Another option for transforming is that you could take the cubed root or whatever root of the y value and produce a scatter plot with a linear form. So we could have taken the cube root of their weights, and so we could actually use length to pick the cube root of weight, which we could then cube and figure out. And in both cases, we end up with a linear relationship. So the previous example shows the relationship between length and the cube root of weight is roughly linear for Atlantic rockfish. Here, a computer output from the linear regression analysis of y equals cube root of weight versus x length, we get these coefficients. Now, of course, it's important to remember that we're predicting cube root of weight. So give the equation of the least squares regression line, define any variables that you use. So it would be this y-intercept plus that slope times x equals the cube root of weight. So let's show that here. Y-intercept plus slope times length is equal to the cube root of weight. And so suppose a contestant in the fishing tournament catches an Atlantic Ocean rockfish that's 36 centimeters long. Use the model to predict, so we can plug in length, multiply that, and then we end up just cubing in the end. So we get that 8.856, and then we cube it to get that same 694.6 grams. So to achieve linearity when working with a power model, the form y equals a times x to the p, you can transform the data by either raising the values of the explanatory variable to the power and plot the points, the appropriate power, or you can take the pth root, whatever the power needs to be, take that root of the values of the response variable and plot the points x and whatever that root is of y. When transferring the data that follow a power model, what if you don't have no idea what p to use? Well, another option is a scatter plot of logarithms of both variables should produce a linear pattern. And so that may seem kind of weird. We could either take the proper power of the x or the proper root of the y, or we could just take a log of both and it'll work out no matter what. And this is because if we take the original power function, and if we take the logarithm of both sides, which would still be true, so this would still be true, and then we can use some logarithm rules here, so we can actually split this up into log a plus log x to the p, and then there's this rule where we can bring that p out front. What we end up with here is a linear relationship between log x, p is just a constant, log a is a constant, and y. And so if you do that with this data, we'll end up with a linear relationship. So in the preceding example, we used powers and roots to find a model for predicting the weight of an Atlantic Ocean rockfish from its length. We still expect a power model to form the weight is equal to the a times length cubed based on geometry. Here, once again, is a scatter plot of the data from the local marine research lab. So we see our data is curved, and they're plotting length and weight against length. And then they took the logarithm with base 10. It really doesn't actually matter what base you use. Those logarithm rules work no matter what the base is. But we took the logarithm base 10 of the values for both variables. Here's the same computer output for a linear regression analysis of the transformed data. And so they did log length and log weight. And so we have this regression analysis. And we're predicting log weight from log length. And it works out. We get a nice strong relationship again. So based on the output, explain why it would be reasonable to use a power model to describe the relationship between weight and length for Atlantic Ocean rockfish. So the scatter plot of log weight versus log length had a linear form, and the residual plot shows a fairly random scatter of points about the residual line. So a pattern model seems reasonable here. Also, we see that really strong R squared. Give the equation of the least squares regression line. Be sure to define any variables that you use. So again, we're predicting log weight from log length using that y-intercept and that slope. So we get that prediction equation. And you can then plug in the length into that and take the logarithm and so on, plug in the 36 and get our prediction. So we plug in 36 into that log of 36, multiply that, add that, you get this value. And so you have log weight equals this, and so we can convert this to exponential form where it's 10 to that power. So logarithm, remember, says what power goes on 10 to give me the predicted weight, and so the answer is 2.8. So you do 10 to the 2.8 to get the predicted weight, and we get the predicted weight of 702. And it's a little bit off, but that's just from rounding error. That is our proper prediction.